Hey there. I'd like to go through some examples of calculating limits. Um, let's start with one that we did in class. I'd like to go through it a little bit more carefully. Let's look at the limit as h goes to 0 of 3 plus h squared minus 9 divided by h. The reason why this is a good example for us to do is because we'll be seeing a lot more examples like this when we define the derivative. So here's our goal. Our goal is to show that this limit is equal to something and figure out what that something is. If you look at this equation, if we tried, it's a rational function of h. If we try to plug in h equals 0, we get 3 plus 0 squared, so 9 minus 9 divided by 0. So if we try direct substitution, we get 0 over 0. And this is telling us that this is indeterminate form. And because it's 0 over 0, that's telling us we need to use some calculation, if possible. Okay, so what we see here, maybe we should do some expansion. Let's expand 3 plus h squared. So this is 3 plus h times 3 plus h, which is 9 plus 6h plus h squared. And so this limit is equal to the limit as h goes to 0 of 9 plus 6h plus h squared minus 9 divided by h. The 9 minus 9 is 0, so we get the limit as h goes to 0 of 6h plus h squared over h. Now, in order to simplify this, we can see that we can divide by h in the numerator and the denominator. But let's be careful about that. So we get the limit as h goes to 0. We'll factor out an h in the numerator, h times 6 plus h divided by h. And now here comes where we're using the fact that we have a limit. So we'd like to divide the numerator and the denominator by h, but we can't just say that is equal to 6 plus h because they're not the same function. We talked about that in class. When you have functions that are defined on different domains, they're not exactly the same function. But because we're looking at a limit when h goes to 0, then when we don't have h is equal to 0, those two expressions are equal. So this limit is indeed equal to the limit as h goes to 0 of 6 plus h, because in a limit, h is not equal to 0. So when you're talking about this limit as h goes to 0, we don't actually care about what's happening exactly at 0. And that's exactly what's happening when we try to cancel the h in the numerator and the denominator. And now we have an expression. We have an expression that says the limit as h goes to 0 of 6 plus h. And now we look at the 6 plus h. That is an expression that's a polynomial. I mean, it's a line, but it's an example of a polynomial. And it's defined for all values of h. And so because this is a function that's defined for all values of h, then we can use direct substitution. So then use direct substitution to get that. We can plug in h is equal to 0. We get this is equal to 6 plus 0, which is equal to 6. So this limit as h goes to 0 of that rational function is equal to 6. All right. So that's one example. That's when you have an expression that gives you 0 over 0. and you need to do some expansion and simplification before you can calculate the value. Here's another example. Let's look at the limit as x goes to 4 of the square root of x minus 2 divided by x minus 4. Okay, so the first thing you should always do is try direct substitution. Plug in x equals 4. We get square root of 4 minus 2 divided by 4 minus 4, which is 2 minus 2 over 4 minus 4, which is 0 over 0. All right, so that's a clue that we need to do some sort of calculation. Need some calculation. Okay, so what's the calculation we can do here? Well, when you have a square root of something plus something, or a square root of something minus something, one of the things that you need to do is you can try a rationalizing. And in this case, we're going to be rationalizing the numerator, which is a little bit strange. You're thinking about rationalizing a denominator, but in this case, the place where we have a square root of x plus something or square root of x minus something is in the numerator. So what we'll do is we'll take our expression, and so square root of x minus 2 over x minus 4, and what we're going to do is we're going to multiply the numerator and the denominator by square root of x plus 2. All right, so how do we know that we had to multiply and divide by that thing? When you have a square root of something minus something, you always multiply by square root of something plus something, and vice versa. So when we do this, so the reason why we're doing this is because when we do this, we get square root of x minus 2 times square root of x plus 2 divided by, now I'm not actually going to multiply this out because that's going to make things more complicated in the denominator. But in the numerator, we have something that looks like a minus b times a plus b, which we know is equal to a squared minus b squared. So let's do that expansion. So I forgot my limit here. That's a no-no. Keep your limit here. So limit as x goes to 4. And the numerator now becomes square root of x squared minus 2 squared over x minus 4, square root of x plus 2. And so this is equal to the limit as x goes to 4 of x minus 4 over x minus 4 times square root of x plus 2. Okay, and then this is telling you that you're on the right track, right? You see now something that you can cancel in the numerator and the denominator. And again, that's because this limit is not, we're not actually looking at what happens when x is equal to 4. When x is equal to 4, we have a 0 over 0. But this limit now becomes the limit as x goes to 4 of 1 divided by the square root of x plus 2. These x minus 4's cancel. So then this becomes the limit as x goes to 4 of 1 divided by square root of 4 plus 2. Oops, I used the limit, so I don't have a limit anymore. So then this becomes 1 over 2 plus 2, which is 1/4. So this limit that we needed to calculate, the final answer is 1/4. All right, let me give you another example. So those are all ways that we can show that a limit does exist. If we wanted to show that a limit doesn't exist, we can show that the limits on two different sides are different. So when you have a piecewise defined function, you may need to show that its one-sided limits agree or disagree. If they agree, then that shows that the limit exists. If they disagree, then that shows the limit doesn't exist. So that's like our example last time, where we have a line and then a parabola. At this point, we can calculate that the limit exists on the left side, the limit exists on the right side, and they match. But an example where the limit doesn't exist is if you have a function on one side and a function on the other side, and their limits are different. So, for example, we might want to prove that the limit as x goes to 0 of the absolute value of x over x does not exist. One second. So, to prove that this limit doesn't exist, let's write down what the absolute value of x is. So this absolute value of x function is negative x on the left side of 0 and positive x on the right side of 0. So the absolute value of x is equal to negative x when x is less than 0, positive x when x is greater than 0. And what's happening at 0? Well, because we're talking about the limit, it doesn't really matter. But in both cases, they agree. So we can say greater than or equal to 0 here. Negative 0 is equal to 0. So it doesn't really matter where we put that equal sign. But this is a definition of the absolute value of x. And so this is a piecewise defined function. It has different rules depending on the domain, where in the domain you are. So now let's look at the absolute value of x divided by x. Well, when x is less than 0, we get negative x divided by x, which is negative 1. So that's when x is less than 0. When x is greater than 0, we get x divided by x, which is equal to positive 1. And when x equals 0, it's undefined, because you can't have anything divided by 0. So this should look familiar in terms of one of the oracles that we did in class. This is that oracle that excuse me, that oracle that had different values depending on whether you were positive or negative. And if we want to show that the limit does not exist, then we need to consider the left hand limit and the right hand limit. Okay, so how do we do that? Well, we say, what is the limit as x approaches 0 on the negative side, or the left-hand side, of absolute value of x divided by x? Well, this limit is going to be what happens when x is equal to 0. So this is actually the limit as x goes to 0 on the negative side of the function negative 1. Okay? Because all values less than 0 all look like negative 1. And because they all look like negative 1, then we're just going to say that the value of this limit is negative 1 because the value is 0 all this way. Sorry, the value is negative 1 all the way up until you get to 0, no matter how close you get to 0. Similarly, the limit on the positive side, the right-hand limit, the limit as x goes to 0 on the positive side of the absolute value of x divided by x, is the limit as x goes to 0 on the positive side. Now we're in this case. Now we're approaching from this direction, and the definition of this piecewise defined function is equal to 1. And so what is the limit as x goes to 0 on the positive side if the values are always 1? Well, the answer is 1. And so what we would say is, since the limits, the two one-sided limits, are different, the limit as x goes to 0 of f of x, or absolute value of x over x, does not exist. Okay, so this is an example of a situation in which the left-sided limit, the left-hand limit exists, where the right-hand limit exists, but because they don't agree, the whole limit, the limit of the function, doesn't exist at that point. Let me bring in one last example, and we're going to develop this a bit further when we talk about the squeeze theorem. But for now, what we're going to look at is we're going to look at the sine of x over x, the limit as x goes to 0 of sine of x divided by x. Now, again, we can try direct substitution. When we try direct substitution, we get sine, so direct substitution gives you 0 over 0. And so we cannot just do direct substitution. There's techniques from later on in calculus that will help us be able to do this, and we're going to use the squeeze theorem in the coming days to talk about this. But let's first just look at the picture of what this looks like. If you should use Desmos or use your graphing calculator. If you do that, you start to see that this function goes closer and closer to x equals 1 at when x is, goes closer and closer to y is equal to 1 when x is equal to 0. So for now, what I'd like you to do is just take as a fact that this limit as x goes to 0 of sine of x over x is equal to 1. We'll prove it shortly. But what this will allow us to do is to answer other questions, like what is the limit as x goes to 0 of sine of 4x over 7x. Okay, so when you see a situation like this, where you have a sine of 4x over 7x, then what you want to do is you want to convert this into an equation that looks a lot like this one up here. So what we'll do is we'll say, we'll rewrite as the limit as x goes to 0 of sine of 4x, and what we really want on the denominator is 4x. So we will write this as 4x. Now we'll write this as, so 7x, but then we want to multiply by 4 in the numerator and the denominator. So this is equal to this limit. The reason why we multiply by 4 in the numerator and the denominator is because now we can reorganize the numerator and the denominator. We can put the 4 in the front here, 4 sine of 4x, and we can put the 7 here, and we can put the 4x in the denominator. So now what we have is we have some constant times sine of something over something. And so this is going to be equal to 4/7 times the limit as x goes to 0 of sine of 4x over 4x. And so the key observation now is that as x goes to 0, so does 4x. So as x goes to 0, so does 4x goes to 0. And because of that, and because we know that the sine of anything, maybe what we should do is we should write this as sine of theta over theta. If we think of theta is equal to 4x, then what we're seeing is that this limit, because it has the same thing inside the sine as in the denominator, then this limit is equal to 1. So the final answer here is 4/7 times 1, which is 4/7, because this limit in this rectangle goes to 1. This also lets us do examples like the limit as x goes to 0 of tangent of 3x divided by sine of 6x. Because what we can do is we can say tangent of 3x is equal to sine of 3x divided by cosine of 3x times 1 divided by sine of 6x. All right, limit as x goes to 0. Now this may not seem like it's an improvement, but it is, because we're still going to massage our expression into things looking like sine of theta over theta. So I'm going to multiply and divide. So I'm going to actually bring the 1 over cosine of 3x out. I'm going to write this as sine of 3x over something, and then sine of 6x, 1 over that. But I'm going to multiply and divide by x. And by doing that, this starts to be able to be massaged into something that we know. So this sine of 3x, we know that we need to now have a 3x in the numerator and in the denominator. So we need to have a 3x in the denominator, so we multiply and divide by 3. Similarly, we need to multiply and divide by 6 for the last expression. And then let's bring everything out, so we get the limit as x goes to 0. We have an extra 3 here. We have an extra 6 here. So let me just bring those outside everything. So 3 divided by 6. I have a 1 over cosine of 3x. I have a limit as x goes to 0 of sine of 3x over 3x. And I have a limit as x goes to 0 of 6x over sine of 6x. Okay, we're almost there. This last expression, this is 1 divided by, so this is the limit as x goes to 0 of 1 divided by sine of 6x over 6x. This is the limit as x goes to 0 of sine of 3x over 3x. And this is 1/2 limit as x goes to 0 of 1 over cosine of 3x. Okay, now each of these limits we can do. So when x equals 0, we can plug this in. We get 1 divided by cosine of 0, which is 1. We get the limit as x goes to 0 of a sine of 3x over 3x is also equal to 1. And then the limit as x goes to 0 of this is 1 divided by 1. So the final answer is 1/2. Okay, so the key knowledge that you need when you're approaching a limit that looks like this is that you need to break it down into such a way that you can apply this piece of knowledge that the limit as x goes to 0 of sine of, limit as theta goes to 0 of sine of theta over theta is equal to 1. All right, so this should give you all that you need to know to be able to complete the web work assignment and most of the limits that come up for you. Feel free to post any questions that you have on our discussion board. Looking forward to hearing where I can be of more assistance. All right, talk to you later. Bye.